Welcome. Continuing the study equation the tangent plane in normal line. In this video, we're going to continue solving examples. In this example, we're going to find the equation of the tangent plane in normal line to a given surface, which is 1 by 4x squared plus y squared plus 1 by 9 z squared is equal to 3. An interesting fact is, in the end of this video, I'm going to show you what is the 3D representation of what we are going to find as we solve this exercise. So you're going to see exactly what is the surface and what is the plane that you're going to find its equation. So first thing is that this surface is given by a function which is a function of x, y and z. So we have a function f of x, y and z. This is 1 by 4 x squared. This is how we can represent this function, just taking the 2 input inside and then it's going to be equal to 0, or we can just say this is equal to our function. So the first thing that we have to do is that we have to remember that when we want to find this kind of we want to find the tangent plane in normal line of a surface, we are going to be forced to find the partial derivative of this function with respect to x, with respect to y and with respect to z. Always we are going to find these things aside, so we are going to have del f by del x, which is partial derivative of this function with respect to x, and partial derivative of this function with respect to x is just you only have this term which has x. Here you can see which is x, and because this is the power rule, we're going to have 2x by 4, which is equal to x by 2. Then also going to find del by del y. This function with respect to y, which is also power rule, we're going to have 2y, and with respect to z. So when we're going to find the partial derivative of this function with respect to z, this is also power rule, so we're going to have 2z by 9. So we have found the partial derivative of this function with respect to x, y and z. So the next thing to do is that we have to find what is the value of these partial derivatives at this given point, because this is the point in which you're going to find the intersection between the plane, the line and the surface. So to do that, what you do is, in this partial derivative with respect to x, you replace the value of x by the coordinate of x. Likewise for y, with the coordinate of y, and z coordinate of z. So this here is a coordinate of x, this is a coordinate of y, and this is a coordinate of z. So what you can say is that del f by del x at the point P, and you know that in the point P the value of x is minus 2, this is going to give us, here we have x by 2, so we're going to have minus 2, I'm replacing x by 2 divided by 2. This x will be replaced by the coordinate minus 2. So what you're going to have, minus 1. We come now for y at the point P. So we know that this function, derivative of this function with respect to y, the partial derivative was 2y, but our y is 1, so we're going to have 2 into 1 because our coordinate is 1, which is going to give us 2. And lastly, partial derivative with respect to z at the point P, and we know that z is equal to minus 3 at that point P. So coming here to the partial derivative, we are going to have 2 into minus 3 divided by 9. This is going to give us, this is going to be minus 6 by 2, then divide them by 3, so we're going to have minus 2 by 3. So now we have found what is the function, what is the partial derivative of these functions at a given point, and we have found its values. The next thing to do is just to have to remember the formula to find the equation of the tangent plane at that given point. And equation of tangent plane, and just I'm going to write ETP, is equal to partial derivative of this function with respect to x at that point P into x minus the coordinate of x, but the coordinate of x here is minus 2, so we're going to have here minus and minus going to become plus 2, plus the partial derivative of this function with respect to y into y minus the coordinate of y, which is 1, plus partial derivative of this function with respect to z, and have z minus the argument of z here is minus 3, so we're going to have minus and minus becomes plus, so I have plus 3, and then all of this is going to be 0. So now what we do is you have to replace these partial derivatives here at this point P. This is all at point P. We have to replace by the values that we have found, and these values are here. So for this first part, we're going to have minus 1 into x plus 2 plus the second part, we're going to have 2, which is the value of this function with respect to y, so this is going to be 2 into y minus 1, and the later part we're going to have minus 2 by 3 into z plus 3. all of this is equal to 0, just replacing these values by the actual values at that given point. So the next thing that we have to do now, we have to apply distribution, in which we're going to find what is the value of this expression, which is going to give us the equation that we want to find. So what we're going to have, taking this here, here, and then this here, here, then likewise. We multiplied all of this function by 3 in a way that you are trying to eliminate this denominator here on this 2z by 3. So that's why we are going to have 3, 3, 3 here and 3 here. This is just for simplification purpose. Minus 3x plus 6y minus 2z minus 18 is equal to 0. So if you want to make it more beautiful, what we can just say is that we have multiplying this, all of this by minus, we're going to multiply this by minus 1 and also this side by minus 1. So in the end of the day, what you're going to have is 3x plus 6y, this is negative, this is positive 3x, plus this becomes negative, minus 6y plus 2z plus 18 is equal to 0. So this is the equation of the tangent plane. And now what you're going to find is the equation of the normal line. So have here equation of normal line. So to find the equation of the normal line, we have an equation in which what you're going to have is x minus the coordinate of x divided by that partial derivative with respect to x, which is also equal to y minus y1 divided by the partial derivative with respect to y, this is x, which is also equal to z minus that coordinate of z divided by del f by del z. Now replacing these values, what I want to have is for x, we know that the derivative of x at that point is minus 1 and the coordinate of x is minus 2. So we are going to have x plus 2 minus and minus becomes plus, and then this all is going to become minus 1, which is there. Minus 1 is equal to y minus 1 divided by, this becomes 2, and equal to z plus 3, because coordinate of z is negative, divided by this here, we are going to have minus 2 by 3, which were the partial derivatives of this function at that given point. So now you may be wondering, what does actually this equation gives us and what does actually this thing tells us, and what actually is the surface that we are finding, that we are using to find its tangent plane. So the exercise we are solving is basically this. Here you can see in this animation that you have a point of intersection between this surface and this plane here. So this is the surface that was represented by that equation that we had in our exercise, and this plane here is the plane in which we have found its coordinates, we have found its equation, and that point was given to us because it's only on that point in that line which he passed to that point, what we were given, that allows us to find the point of intersection between this surface and this tangent plane. So the physical interpretation of what we just solved is this.